Welcome back. Today we're going to make that connection between integration and the area under a curve. And we'll actually be able to find the area under a curve. If you remember section 6.3, we talked about approximating the area. And we looked at that function, f of x equaled x squared plus 2. And we went from 1 to 5 in 4 sections generally. So we looked at this region in here. And we talked about how we could approximate that area using some of the figures that we know the area of, namely the rectangle and the trapezoid. Well, if at the end of that section we talked about creating an infinite number of sections in there, and when I talk about an infinite number of sections, it means that each slice is going to be just a sliver of a rectangle. And if I take the limit as n goes to infinity of that region, that's going to give me the area. What does that look like? Well, ultimately, the integration of a function gives us the area under a curve. And we call this definite integration, or the fundamental theorem of calculus. So if I integrate from a to b, remember a and b are my endpoints, my lower bound and my upper bound of my region, of the function f of x dx, I'm going to get the integration of that value. I can plug in a and b into my function, take f of b minus f of a, and it's going to give me the actual area of that region. So what does that look like? Well, let's go ahead and look at that example that we looked at. This was x squared plus 2. Let's look at this function, x squared plus 2, if we integrate it from 1 to 5 dx. So we can integrate x squared. We know that integration is x to the third over 3. The integration of 2 is 2x plus c. And we're going to put a bar. Since we've integrated this, we don't want to lose that we're going from 1 to 5. So we're going to take this 1 and 5 and we're going to place it at the end of our integration. So now what I'm going to do is I'm going to take my 5, my upper bound, I'm going to plug it in for my x's, and then I'm going to plug in my 1 for my x's and subtract those two values. So if I plug in my 5, I get 125 thirds plus 10 plus c, minus, if I plug in my 1, I get 1/3 plus 2 plus c. Simplifying this, I can multiply that negative through. So I get 125 thirds plus 10 plus c minus 1/3 minus 2 minus c. Now we've talked about this c value before being very fluid. But notice this c, when we plugged in the 5, there was no x with it. And when I plugged in 1, there was no x with it. So this c value is actually the same. It's a constant c value. So c minus c, that's actually going to cancel each other out. So I get 125 thirds plus 10 minus 1/3 minus 2. And that's going to give me a value of 49 1/3 units. And that's going to be the actual area of this region. Now, if we remember from when we did the approximations, we saw that we had 49 from the midpoint and we had 50 from the trapezoidal. So 49 1/3 should make pretty good sense to us. As well as it's between that upper bound and the lower bound. Remember, I believe it was 38 and 60. So in example 2, we can go ahead and do this again. We're going to integrate from 1 to 3. So our lower bound is 1, our upper bound is 3, of 4 over x dx. If I go ahead and integrate that, 4 over x, we should see as 4 natural logs of the absolute value of x. And we're going from 1 to 3. If I plug in my 3, I have 4 natural logs of the absolute value of 3 plus c, minus, plugging in my 1, I get 4 natural logs of the absolute value of 1 plus c. Again, I can multiply that negative through. So I have 4 natural logs of 3 plus c minus 4 natural logs of 1 minus c. Again, these c values, there was no x value. See there, there's no x value with that, so these c's are still going to be constant, and they're going to be the same constant, so they're going to cancel each other out. So now I have 4 natural logs of 3 minus 4 natural logs of 1. I know the natural log of 1 is 0. 4 times 0 is 0. So I get 4 natural logs of 3 minus 0, or 4 natural logs of 3. I could approximate this using the calculator if I wish. So 4 natural logs of 3 gives me approximately 4.394. And that would be the area of that region. So with the second example, hopefully we see that that c value is canceling out. And we're always going to see that with a definite integration, whenever we have numbers out here, our a and our b value, that c value will always cancel out for ourselves. So we really don't have to worry about that c value anymore when we do our integration. From here, we're just going to go ahead and do some more problems, some more practice, and see what we end up with here. So if I integrate 1 to 3 of 3 over x squared dx, I'm going to bring that x squared to the top. So I'm going to go from 1 to 3 of 3x to the negative second dx. Integrating at 3x to the negative first over negative 1 from 1 to 3. Notice I didn't put that c value in there. I can go ahead and clean this up. I get negative 3. X to the negative first goes to the bottom as a positive, or x to the positive 1 from 1 to 3. Again, we can go ahead and plug in the 3 and then plug in the 1. So we're finding f of 3 minus f of 1. Should be capital F's there. So I plug in 3, I get negative 3 over 3, minus, plug in my 1, I get negative 3 over 1. So I have negative 1 plus 3, or 2 units. And that gives me my area. Example 4, we have x times x minus 1 from 0 to 3 dx. So again, we can distribute that x. We could do some u substitution with these if you want, but honestly, if it's an easy multiplication, I would suggest multiplying it out, not even worrying about the u substitution. So if we do that, we have x squared minus x. We can integrate. We have x to the third over 3 minus x squared over 2 from 0 to 3. Plugging in my 3, we get 3 to the third, which is 27 thirds, minus 3 squared is 9 over 2, minus, plug in the 0, we get 0 over 3 minus 0 over 2, which is 0. So I get 27 thirds, which is 9 minus 9 halves. And 9 minus 9 halves gives us a value of 9 halves, or 4.5 if you wish. And that again gives us our area. I have just one more example, so it'll be kind of a quick day here for us. Example 5, we're going from negative 1 to 1 of x squared plus 1 dx. So we can integrate. We end up with x to the third over 3 plus x from negative 1 to 1. Plugging in the 1, we have 1/3 plus 1, minus, plugging in the negative 1, we get negative 1/3 minus 1. Simplifying this, we have 1/3 plus 1 plus 1/3 plus 1, which gives us 2 2/3. And that gives us our area again. And that is our definite integration, or the fundamental theorem of calculus.